Hi, my name is Salazar Verma, and today I'll be investigating two addition polymers, polyethylene or polyethene or polyvinyl chloride or PVC. I will explain and model the production process and structure of the addition polymer while also linking the structure to the properties and applications in the real world. Before we begin, let's examine some chemistry terminology that I'll be using throughout the video. Polymerization is the process when subunits called monomers are repeated and combined to form a polymer. Polymers are often referred to as macromolecules because they have very large molar masses. Ethene or ethylene is a hydrocarbon belonging to the homologous series called alkenes with a double bond between two carbon atoms, hence the suffix of -ene. The molecular formula for ethylene is C2H4. An addition reaction is when atoms are added by breaking the highly reactive double bond or triple bond in alkenes and alkynes respectively, and the atoms are added across the bond.
Alright, let's dive in. First, let's discuss the process of polymerization. Initiation is when an initiator is applied to the monomer and it breaks the reactive double bond of the monomer and attaches to one bonding site and leaving the other bonding site open for other monomers to connect. This molecule is now a free radical. Propagation is when another monomer attaches to the bonding site of the first free radical monomer, thus making a combined radical. This process continues to rapidly increase chain length. Third step. Termination is when the reaction is stopped. The two polymer chains combine, causing the radicals to become unreactive.
The first polymer I will investigate is polyethylene or PE. Over 80 million tons of polyethylene is manufactured each year, making it the world's most important plastic. Polyethylene is a synthetic polymer. Polyethylene can be produced in many different forms depending on the reaction conditions used. The two most common types, high-density polyethylene and low-density polyethylene, and there are other forms that are less common. Ultra-low-density polyethylene, linear low-density polyethylene, etc. Different production methods with different reaction conditions lead to the different structures which result in polyethylene with different properties and uses. The general structural formula for polyethylene is this. And N represents any number of ethylene molecules being repeated in the polymer chain. Polyethylene. High-density polyethylene is very dense relative to low-density polyethylene. For what production process is used to achieve a molecular structure that leads to the property of high density and other properties? First of all, the monomer that is required is called ethylene and is obtained through fractional distillation of crude oil. The product of this is naphtha. Naphtha is then thermally cracked to make ethylene. High-density polyethylene is produced by different processes such as slurry process, solution process, and gas phase process, all operating at low pressures of 10 to 80 atmospheres in the presence of Ziegler-Natta or inorganic Phillips catalysts. The temperatures range between 77 to 147 degrees Celsius. Hydrogen is added to the process to control the chain length of the polymer. The slurry process is very similar to the original process called the Ziegler-Natta process. The new process is more efficient and effective in production of high-density polyethylene from the monomer ethylene. In this process, the liquid form of hydrocarbon is mixed with the Ziegler-Natta catalyst and hydrogen, which is then passed through the slurry reactor under low pressure of only a few atmospheres and at a temperature of 60 degrees Celsius. The catalyst used in this reaction is a mixture of titanium chloride and trialkyl aluminum compound. Out comes the polymer chain. The gas phase process uses a Phillips catalyst and the ethene and hydrogen are passed through a fixed bed reactor. That is another type of reaction. Both the slurry and gas phase process yield linear polymer chains that form carbon chains with no branches. This structure allows the polymer to pack more closely together in the crystalline structure, thus the name high-density polyethylene. There are also strong dispersion forces between the chains leading to a higher melting and boiling point of the polymer. HDPE is tougher, denser, more rigid compared to LDPE because LDPE has many branch chains which leads to more amorphous regions forming, which means less dense packing, weaker dispersion forces, allowing the polymer to be more flexible. Polyethylene is suitable for containers as they have long hydrocarbon chains that make them lightweight and cheap to transport. Polyethylene has non-polar intramolecular forces because of the symmetry of the molecule and the similar electronegativities of the atoms, leading to insolubility in water, as water is polar. They are also chemically inert, meaning that they don't react with their contents. HDPE is used to make buckets, bowls, water pipes, petrol tanks, bottles, rigid toys, rubbish bins, and kitchen utensils because of their linear chains that are durable, hard, and don't break easily. If the polymer is cross-linked, that makes it even stronger and rigid. Let's examine polyvinyl chloride or PVC. What's actually involved in the production of PVC? First of all, the monomer that is required to form PVC is called vinyl chloride monomer, VCM, or chloroethene. To obtain this monomer, ethene undergoes addition reaction with chlorine atoms to form 1,2-dichloroethane. 1,2-dichloroethane is then passed rapidly through metal tubes at 650 Kelvin. It is then cracked to eliminate hydrogen chloride, which is a product of this reaction. The leftover product is VCM, which is required for the polymerization of PVC. PVC in its pure form is hard and brittle, even though it has an amorphous structure because of the chlorine atoms not allowing the polymer chain to pack closely together. PVC also decomposes under heat and light. It is also very stiff because of the large electronegative chlorine atom in the monomer, which creates a dipole-dipole intramolecular bond, attracting the electrons towards itself. These properties make PVC very ineffective and can't be used for many things like outdoor plastics because PVC decomposes in UV light to release CO free radicals. This is harmful as it can categorically degrade the ozone layer. However, adding different types of compounds to PVC can alter its properties, thus allowing it to become more useful in the real world. This will be further discussed later on. But first, let's investigate the process of addition polymerization of PVC. VCM is gas at room temperature and pressure, and the reaction is carried out under pressure of 13 atmospheres and temperature of 325 to 350 Kelvin to keep the monomer in liquid form. An organic peroxide initiator is required to start the polymerization process. PVC is then formed into small particles, and when the reaction is stopped, drying allows for the final product of PVC resin to form. Here you can see the PVC chain with chlorine atoms and branches on the sides and hydrogens on the end. As I mentioned earlier, adding additives to PVC alters the structure of the polymer and allows for it to be more useful. For example, adding a plasticizer leads to weaker dispersion forces because the molecules are held further apart. This allows PVC to be more flexible, and this property allows it for it to be used for flexible pipes and electrical cables. Adding heat stabilizer compounds like organophosphites and phenolic antioxidants to PVC makes it suitable to use for hot water pipes and cars, as it will be heat resistant.
The main difference between the structure of PVC and HDPE is that PVC has chlorine atoms branched off the main chain, making it an amorphous structure. As mentioned before, chlorine is highly electronegative, so it pulls electrons towards itself, creating a dipole-dipole polar bond. This molecular structure and the large size and mass of chlorine leads to properties like stiff, hard, and brittle. On the other hand, high-density polyethylene has ethylene linked to each other, and they are nonpolar with no branch chains, allowing for a crystalline structure to form and a denser formation between chains.
My model's benefits are, for example, the big size of the model allows for anyone to easily understand and visualize the complex structure of the molecule and process being shown. My models allow chemical processes that occur at atomic level to be understood physically. However, my models that I've presented have some limitations. For example, the intermolecular bonds aren't actually sticks. However, they are invisible forces of attraction. The atoms in the molecules aren't actually solid balls like marshmallows. Instead, they are much more complex with a nucleus with protons and orbitals with electrons. My models are not to scale because real ethylene or vinyl chloride molecules are very small compared to my model, and in my models, the sizes are very large compared to hydrogen and carbon in real life. My models are effective in the way that they presented a way of showing the correct process of polymerization of PVC and PE, and showed the structure in a simple way, yet not missing any important details. Overall, my models of PVC and PE could be used as good teaching and learning tools to help understand the complex process of polymerization in a simpler and fun way.